Welcome to our video on Big O notation. We're going to be talking about how we describe different algorithms in code and how we're going to go about kind of seeing what this really ultimately looks like, how we talk about the workload of our processes and what we've written in our code. This is going to be mostly theory. There's not a lot of code on this actual document, but again, in tandem with a lot of the stuff that we've been discussing, I think it should make a lot of sense. So we're gonna go ahead and get started. First of all, that changed my scene. I want to change the slides. Thank you. All right, so we're gonna say a little bit about memory. So first of all, again, we've talked about this several times at this point. Think of memory as a bunch of computer boxes. If I say my integer equals 30, that's valid Python. It's obviously not valid JavaScript, but you get the idea. I declare a variable, I call it 30, and it has a memory address somewhere, right? And it looks something along these lines. Especially in Python, you can print this kind of data out. JavaScript won't let us do that. A big part of why JavaScript won't let us do that is because we don't want people able to write JavaScript in our browser. Like if we run a website, then JavaScript to run and it can access our computer's memory directly. We want to abstract that away. And so the JavaScript developers, the people who wrote JavaScript, specifically made sure that if you visit my website can't read your computer's memory. I can utilize it in the browser, but I can't directly access it or manipulate it. Python, on the other hand, does not operate this way, and so we can use those direct addresses, which is part of why we're using Python for this lecture. Obviously, you don't need to know Python. Just understand I have a variable called myInt. I've set it equal to 30, and it's got this memory location 0x7364, blah, blah, blah. Okay, that's where it lives. That's its mailing address, so to speak. Big O notation, and we'll see why this stuff this will come back in again in just a moment here. But Big O notation is the way computer engineers and super smart math nerds who do this stuff without computers, they just like to play with the ideas and concepts here. It's how they notate how much time and memory a function will end up taking. So generally, speed is prioritized. You can see like how fast your code runs, how many steps it takes ultimately. And so finding the fastest way of solving a problem is what Big O is all about. Usually, a problem will have multiple ways of approaching and solving it, and optimizing the solution is going to be the important part of writing algorithms, right? So it's usually not super hard to find a solution, but then going from there and refactoring our code and trying to find something better, that's going to be a valuable part of our time and what we end up doing. So just some examples of what we're talking about here, right? When we can give a computer a list, right? So a list is, again, a whole bunch, there's values in each of these cells. When we give a computer a list, it can't look at multiple items on the list at once, right? It's electricity, it uses zeros and ones, it can only either have a value or not have a value, and it can only run through one thing at a time, unless you have a computer with multiple processors, which is normal, but we're not going to get that detailed into how our computers work. But essentially, we're going to just, for practical purposes, say that our computer can't look at every item in an array at the same time. It has to go one at a time and loop through. And so it will hold other ones in memory while it's working, but it works on one item at a time, right? So like when we say add 1 to every item in an array, it's going to go to the first one and add 1, and then it's going to go to the next one and add 1, and then go to the next one and add 1, and then go to the next one and add 1. It can't do it to all of them at once. And that's what we're talking about here, right? Understanding what's going on under the hood that way is extremely important in understanding how to optimize our algorithms. So we've talked about this one before. This is the binary search algorithm, right? But we're going to look at this. We're looking for a specific name. This is just, again, having another kind of review of how algorithms and Big O notation work. We're going to see this in a moment. But you're looking for a specific name in the phone book. There's a few ways to get through there. One would be starting on page 1 and working through each item on the page until you find the letter of the name you're looking for. Is this efficient? Yes or no? Well, if you're looking for Aaron the Aardvark, this is extraordinarily efficient because it's almost immediately that you get that value. But if you're getting Zizok the Zebra and you're going to go through every name in the whole phone book, that's going to take a really long time. And so there's probably a better way that we just get a general average value back faster. And so it's a little bit slower than maybe the optimal algorithm for Aaron the Aardvark. But we can consider, like, our worst case scenario for Zizok the Zebra is going to be with our one at a time. It's called linear search, right? Where you're doing in a line, one next, and then the next, and the next, and the next, compared to binary search. And a linear search, Zizok the Zebra is going to be like however long that dictionary or that phone book is going to take that whole time. A binary search is going to cut it down to like maybe 6 to 8 steps maximum, like major actual steps. And so That's kind of what we're talking about here, right? It's like there's better ways to average figure this out, where the worst case scenario is only going to be, you know, a handful of steps for our best algorithms, whereas our worst case scenario for bad algorithms might be thousands of steps. So that's what we're kind of looking at here. So this is the big O complexity chart. And we're going to talk about what these n's and log n's and other things are. But this is how we notate our algorithmic performance, okay? So first of all, we've got O of n, and that means, so n here is a variable, and n grows or shrinks to however long our array is. So if I've got an array that's 10 items long, that's going to be O of n in order to look at every item in the array, because maybe I pass it an item that's 10 items long, maybe I pass something that's 1,000 items long. N can change, right? But it's going to change at the same rate, okay? If I have to go over every item in an array and it's 10 items long, then way over here on the left, that'll be like 10, or over here it'll be like 1,000, but each thing that I add is just one more iteration, okay? If I have a loop inside of a loop, okay, that means that for every time that I run the outside loop, the inside loop also runs a certain number of times. And that's going to be O of n squared, right? So if I have 10 items, and for every one of those 10 items, I loop over another 10 items, that's 10 times 10. That's 100. That's 10 squared. And so that's why we have this here. We'll see a little bit more of examples of this in a moment. Credit over here to Eric at Big O Cheat Sheets. So this is just a good website here just to kind of look at and get a little familiar with. And so we can see some different data structures, like what we're kind of working through here and how this works. And we've got all of our sorting algorithms and which ones are fastest or shortest. So you remember, and we usually talk about worst for time complexity. We usually look at worst case scenario because we might say, again, oh, Aaron Aardvark, that's a super easy one to find. But most things are not going to be that quick. And so we want to be more concerned with the worst case scenario and optimizing that. And so you have some that are actually quite good. This one, O of nk, radix sort, and you can go and look at the page for what that means, how it works, and can be pretty brutal reading. But Wikipedia actually has really great computer science topics. So if you're ever like, what is this thing? The Wikipedia pages usually are very, very good, especially with like more math-oriented stuff. I want to get the cool cheat sheets, some other stuff. Anyways, this would actually probably be a good read. I haven't read this one, but I've heard good things about it. So anyways, just passing that along too. Not for right now, but once you finish the course. Anyways, so we got all these different worst case scenarios, and you can see some are actually quite bad for worst case. Bubble sort took quite a lot of steps. Insertion sort took less, but still quite a lot of steps. Because with both of those, you'll recall we had a for loop and then a while loop inside the for loop, or vice versa, right? So that's automatically, because there's a loop in a loop, that's going to be O of n squared. Because if I feed it 10 items and it has to go each of those 10 items in the first loop and 2 10 items in the second loop, that's automatically going to be O of n squared. Cool. And merge sort is going to be a little bit better. It's going to be less steps, and we saw that as well, that our merge sort, especially for longer lists, ends up optimizing and ends up being better and less steps than those other ones. So cool, great. Anyways, yeah. Look at this graph. Why would some of these be better than others? Again, you can see obviously that if you pass in 5 items, right, and we're looking at, let's go back a page, 2 pages. If I pass in 5, let's say that like right here is 5, right? So O of n, 5 loops for 5 items. Okay, great. O of 1 is going to be the same thing no matter what, which is great. That's going to be like, I have a function that takes an array and then it just console logs hello world, no matter what. Doesn't matter what you pass into it, it's going to always do the same thing. So that would be O of 1. And well, again, we're talking about, I'm going to explain why these are the way they are in just a moment. And we're going to look more at like kind of the math side of things. So we'll say we've got 5 things. O of n is going to be 5 iterations. If I pass in 5 items to O, to my function, it's going to loop 5 times. However, if I have O of n factorial, which is an atrocious design decision, it will run extremely slowly because 5 items passed into my function will run 120 times, right? Because that was 5 factorial. We talked about that with recursion. 2 raised to the n, this would be 2 to the 5th power. Which I believe would be what? 2, 4, 8, 16, 32. So 32 loops for 5 items. which isn't terrible. It's better than, or it's worse than 25. Well, it's still pretty bad. It's still pretty bad. It's horrible. And again, like you can imagine that if somebody is, say, like let's imagine we're Google, right? And somebody passes in, they Google search for something like pandas, right? That's 6 characters long. This would end up being, where 6 times 120 is, which is a lot, right? That's, like 700-800 loops somewhere in there. That's not good. And then 2 raised to the 6, that's also not good. And that's only with the word pandas, okay? For each letter in there, it has to do a full set of loops, etc. With this kind of deal. That's going to be really bad. Whereas something that's O of n is going to be much faster and a very quick response to say, oh, this is some stuff about pandas. And obviously, if you've got a really long string of things that you're Googling, we're going to want to be looking for some of these better options than some of these. So we'll keep looking at some more of this stuff in a second. So if a computer can only really do one thing at a time, how would that affect what we choose to do with our chart? Because obviously it can't go faster, right? You can't feed your computer more gas and make it go quicker. And so you like can by getting more computers to help with the problem, but that's expensive and not always really a realistic option for us. So some problems cannot be solved with the green or yellow or sometimes even orange lines. Some problems are just plain bad and there's no way to get around it. And so that it's okay if you end up having to do multiple loops for something, but it's always worth considering, is there a more efficient way of doing what I'm trying to do here? So in the phone book example, it was a little harder to see where the memory heavy side of things came into play. So again, if we go back to this website, we've got space complexity, and that's what we're talking about with our memory, okay? And so if I have an array that's 5 items long, then O of n is going to apply here because that array, however many items are in the array is how long it's going to take. That's how much memory it takes, right? 5 items is going to be 5 spots in memory. And most of these are basically that way. So that's cool. And we have some different kind of things going on in the middle of our array. Obviously, like searching our array, like if we go to the 5th item in our array, if we have 10 items in our array, it's going to the 5th item, it's going to be O of n because it's going to have to loop 5 times, right? So if I go to the 5th item, it's going to have to go over the array, start at the beginning, 0th item, 1st, 2nd, 3rd, 4th, because that's index 0 indexing, blah, blah, blah. Anyways, you get the idea. And again, we'll see more of this, and I'll keep pointing this out, especially in our next couple lectures here. But imagine you're sorting through library books. You have 1,000 of them, and you need to alphabetize them and put them away. One way would be to take each book and put it on the shelf, and if you need to, insert the book ahead of what you've already placed into the correct location. Again, we talked about this with our last lecture a little bit too, which I'm glad we did that so that you guys have some more idea of what's going on here. So you're putting the books in kind of one at a time. But you could also think of maybe some other ways of doing this that might be more efficient for maybe the way that you would want to store them, right? But there's always going to be trade-offs. So you say you could make piles of books that start with A, B, C, etc., right? So you have your A books that start with A pile, books that start with B pile. And this would be more memory heavy, right? Like you have to remember which pile is which one and what's in each of those piles, right? But then once you're done with that, you can take the whole pile and sort inside the pile, which is a lot faster than sorting it with the entire set of books, right? So it's easy to say, oh, I've got 100 books that start with A, and sort those themselves, and then just put them all up on the bookshelf immediately. It doesn't take a whole lot of energy to go boop, 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 once those are sorted within themselves, as opposed to one book at a time amongst the whole 1,000 and trying to figure out where that goes. So anyways, it takes less running back and forth, but it does require a little bit more like remembering where those piles are and how much stuff is there. So in both examples, we end up holding bigger pieces of information in memory. In the phone book example, we compare and hold the entire half of the phone book instead of just one name at a time. In the library case, we hold piles of books based on their letter and wait with them until it's time to use them. In both cases, how we use the memory affects how we use the time. Sometimes memory gets ignored for time, but super fast functions take a lot of electricity as well. So that's just another thing to think about. Google's carbon footprint is not good, for example. Anyways, so rules of big O notation: drop constants. Okay, so O of 2n is still just O of n, which doesn't make a lot of sense. I'm actually going to show you an example of why we drop constants in just a moment. But that's part of why we do that. Any kind of looping function, even if it doesn't look like one, is a loop. Okay, think of things like map, where while is another loop, right? That you maybe not be thinking of. You might just think of for loops, but while loops, do while loops, even some things like sorted is secretly a loop or dot sort, okay? Because it's still going to go through our whole array and look through everything and put it in order, okay? And then I want you to think mathematically. If you have a loop inside of a loop, and we're dropping constants, okay? So you might be like, well, one loop runs 5 times and one only runs twice. It's still a loop inside a loop, and we still drop those constants, okay? It's still going to be like n times n, which results in an exponent, right? N squared. And then, again, thinking mathematically, if you have 2 loops together, it like n and then another n, which means it's not, okay, so if they're not nested, if they're not inside of each other, right? So for, let I equal 0, I is less than 5, I plus plus, do some stuff. And then you have a whole nother loop, right? While counter is less than 5, do some stuff, counter plus plus, right? Those are both going to run 5 times. It's not going to run 25 times because they're not inside of each other. They're on the same kind of line. They're not inside. It's not nested. So keep that in mind as well. Nested loops are exponential. Non-nested loops are still just O of n. And then imagine the average performance of your algorithm, right? If we use 10,000 different data inputs, then imagine what the average performance would be. And that's kind of what we're trying to communicate here, right? Give us a ballpark. Let us understand overall why your algorithm is better than mine, right? And again, algorithm doesn't necessarily just mean what we've been doing the last document or two. That can be all of our code, right? Any solution to a problem is technically an algorithm. And so anytime we're writing a function, anytime we're writing code, there is an approach, there's a way that we've decided to solve that problem. And there's lots of different ways of solving most problems, and it's just a matter of what are we optimizing for? Are we looking for the best memory? Are we looking for the best time? Are we looking for whatever, right? It varies. Okay, so you might be wondering, all right, Brandon, why do we just ignore some numbers? It's not precise to say I don't care if we add numbers at the end. It's still just O of n squared. I don't like this, Brandon. Why did the nerds do this to us? It seems very inconsistent for the math nerds to say, oh, the numbers just don't matter. Well, you're not wrong, but again, we're trying to speak in generalities, right? We're trying to just get a ballpark idea of how your algorithm is performing. So I want you to imagine a mathematical equation with a huge exponent, okay? So for example, 5n cubed plus 7n squared plus 5, okay? So now if n equals 1, this is only 5 plus 7 plus 5, which ends up being 17. The 5 at the end here is kind of important right now, right? That the difference between 12 and 17 is actually pretty significant, right? 12 is just shy of 2/3 of 17, so that's a pretty big difference between the two. But if n equals 20, suddenly this is 40,000 plus 2,800 plus 5, right? The difference between 42,805 and 42,800, they look basically the same, right? If you had 42,805 rolls of toilet paper thrown at your house versus 42,800 rolls of toilet paper thrown at your house, you're not going to notice the difference between the two. You're never going to care. Your house is going to get crushed under the giant weight of toilet paper. I don't know why that's the example I gave. I was also thinking about if you just had cartons of eggs in your house. I mean, either way, like that last 5 is not going to matter at this point, whereas a difference between 12 rolls of toilet paper in your yard versus 17, you'll notice the difference, right? Like you could just eyeball and see there's a difference there. Obviously, we'd all prefer 0 toilet paper rolls thrown. Why did I go with that? I don't know. Whatever. Anyways, and if you have 100, we've got 5 million plus 70,000 plus 5, and now the 70,000 is also pretty useless in the grand scheme, right? 5 million 70,000 versus 5 million is really not a huge difference. Again, if you're looking from a distance, right? If you're comparing the populations of a city with 5 million people versus a city with 5,070,000 people, it's going to look almost identical, right? Like you're really not going to be able to tell the difference between these two populations. So it's pretty useless in the grand scheme. So we're really only concerned at the end of the day with n cubed, like whatever the biggest n exponent is, okay? So if it's just n, if it's just one single constant, great, fine, whatever. And I also didn't put like plus n plus 5. I could have had, instead of, because we go cubed, squared, and we skip just a n to the first power here. And then this is n to the 0th power back here with 5. But anyways, point is, we're only really concerned with the biggest number, right? Like speak to me in generalities. The 70,000 plus 5 really aren't going to change that much. So anyways, so that's kind of what we're looking at here. Yeah, the 70,000 is pretty useless in the grand scheme. We don't really care about that. But if we didn't have the cubed n at the beginning, suddenly that 70,000 is important compared to the 5. So then we care about the n squared, right? And also we're more concerned with the scaling. 10,000, if you don't multiply the n squared with 7, so just 10 times 10, it went up a lot faster than 5 because 5 doesn't change at all and it's a constant. And again, we drop those constants from the beginning of things because 7 times 10,000 is not as significant as like the 10 times itself. So anyways, you drop the constants. That's just kind of the way it is. Last thing. All right. So the scaling part applies when you don't know the length of your list. So if I said, and again, this is Python, but you'll be okay. It looks a little different, but we'll see this in text. Okay. So def is like saying function in JavaScript. So function, some func. It doesn't take any parameters. A list equals, and our list is just one item long. For I in a list, print I. This is only going to run one time, right? It's hard coded. The length of a list is established. And so this isn't actually going to be O of n, right? There's a for loop in there, but we know exactly how many times it's going to run. And every time that I call some func, it will always happen the same number of times, okay? So this is for I for let I equals 0, while I is less than length of a list, less than or equals the length of a list, I++, console log I. That's just the Python version of what's happening here. So if you're like, what's going on here? If this is throwing you, please just Slack me and I will send you a copy of the JavaScript version of this function. But our function will not change no matter what data happens around it, right? The only way that the length of this array will change is if the length of a list changes, but we've hard-coded that in there. It's already in the function. It's in concrete. We can't change that. And our function doesn't even take any data, right? So that ends up being fine. It's always going to occur just once. So that would be O of 1. It's a constant. The number of loops that this will do, the length of time that this will run is always the same. We're going to say, okay, it's just going to be always the same no matter what. Alternatively, if I did it this way, right, where I actually passed the array in, again, in Python lists, or arrays are called lists in Python, which is why I keep using that language. But in JavaScript, we pass in an array to this, and if we're going to loop over every item in the array and then log it out, print it out, this would no longer be constant. This would be linear because however long our list is, that's how many times the loop is going to have to happen, right? And so that's why our choices for how to solve our problems are important. We don't always know what our algorithms will be fed. Again, imagine probably the most famous algorithm of all, which is Google's search algorithm, right? And that algorithm is going to be fed who knows how many different things per day, right? And we need Google to operate quickly, kind of no matter what. That's literally why Google, the company, made all of its money early on with the search, was that they've come up with this brilliant idea for how to do that search better. So because our algorithm changes on that input, we just have O of n, where n is the length of the input. And Google obviously works way faster than that. They've got a bunch of ways of parsing out what you feed it and how that's going to work, which is very clever and very cool. But Google Maps, too, same deal. You never know what you're going to get fed with Google Maps, and you just want it to be quick no matter what. Google Maps is actually a really fascinating study in how code works and how things are arranged. All right, cool. Anyways, lab time. We're going to look at some code now, but we're going to do that in the next video. So that is it for this lecture. So that's the theory, and now we're going to look at some other algorithms, some other time and space complexity stuff, and that should be pretty cool. So I will see you in the next lecture. Have a great day.